If Santosh or Devarati are there, can you just confirm if you can see my full screen?
Yes,
okay.
Now we can.
Okay, thanks. All right, so I guess I will start now. We are up to 190 and people will join in. Good morning, everybody. Welcome to this first series of lectures on radiative processes and radiative transfer. I'm Dipanjan Mukherjee from IUCAA, and I will be discussing some of the basic concepts of radiative processes. Of course, the whole topic of radiative processes is extremely fundamentally important to astronomy because astronomy involves observing distant objects. And observing means you have to infer something about them by um, getting the electromagnetic radiation from them. Well, we have another form of radiation nowadays that we are using for astronomy, which is the gravitational wave astronomy, using gravitational waves from distant objects. But predominantly, astronomy has been understanding distant objects through electromagnetic radiation. And there are different kinds of physical mechanisms that give out this radiation. But even before we go into the physical processes that give out the radiation, we have to understand some basic formalism of how to sort of infer the radiative, the total flux and the total energy that you're getting at a given place. And from that, build up a set of mathematical formalism to understand the radiative transfer process. But that is, given something is being emitted at some place and it passes through an intervening medium and finally reaches you at Earth, how would you account for the total amount of energy added, energy lost due to absorption, scattering, etc., into all of this, and then compute the total flux that you would receive as an observer due to some emission mechanism happening far away? So the brief outline of these series of lectures, the 4 lectures would be that in the first lecture today and perhaps a bit of tomorrow, we discuss some of the basic formalisms of radiative transfer. I will not go into the mechanisms yet. So we set up the basic definitions that we use to calibrate the amount of energy that is coming towards you, and some of the basic mathematical derivations of the equations we use to solve the equation of intensity and flux that is coming at a point, and some of its implications. Thereafter, we will go into the details of the radiative processes. Now, I will warn you that the entire course of radiative process, it's quite complicated. It usually takes us about 14 to 20 lectures to cover the entire thing. So what I'll do is, in the remaining few lectures, give you a brief glimpse of the different processes and mechanisms that are involved. And hopefully that will motivate you and or refresh your memories if you have already learned them towards a more astronomy-oriented application of this. Now, some brief guidelines about how the lecture will proceed. Since it's an online Zoom version, it will become quite difficult to manage everyone if you have questions in between the lectures. So what I will do is I will take pauses in between the lecture. I'll take a couple of questions in between the lecture and at the end. Of course, since there are many participants, we may not be able to address all your questions. Use the Google form, and I will try my best to address some of the pressing questions through the Google form in the subsequent lectures. Okay. So the basic texts that I will be following are these. I will add one more. This is a Longueur book by Longueur in 2011. I forgot to mention it here, it seems. But the primary book is Rybicki and Lightman. This is a fundamental book for anyone who does any course in astronomy and on radiative processes. There's a second very interesting book called The Foundations of Radiation Hydrodynamics by Mihalis and Mihalis. This is a bit higher level. but it covers, first of all, very nicely the mathematical foundations of radiative transfer. And more importantly, when you couple radiation with fluids, how to treat the ensuing fluid dynamics of it. And of course, the standard master's level textbooks of electrodynamics like Jackson. Okay. So, firstly, the electromagnetic spectrum. So, as you can understand, we observed the different phenomena happening all around in the universe by collecting the electromagnetic radiation coming from them towards us. But the different kinds of mechanisms emit at a broad range of wavelengths. And I think appreciating this particular slide is very important and fundamental for astronomy. What this shows you is what the different bands or the different wavelengths or frequencies in the electromagnetic spectrum. At which of these frequencies or wavelengths do we actually are able to see the emission right down from the surface of the Earth, and which of these are actually absorbed in our atmosphere? This completely changes how we plan to observe these kind of systems. For example, in early days, when we did not have access to space or even have the more complicated electronic equipments, the primary mode of astronomy was through the optical bands. And as you can understand, the optical bands are completely transparent. So what this slide shows you, the y-axis shows you which of this the amount of transmissibility or what fraction of the radiation is absorbed for a given frequency. So optical band is completely transparent. The atmosphere is completely transparent. So earlier days, starting from Galileo and even others, we could observe the stars and make some tangible signs out of it. But later on, we started to develop more and more sophisticated instruments, and it was found that simply limiting yourself to the observable band or visible bands of radiation is not enough. So I'll not go into the history of it, but starting from the highest frequencies of the lowest wavelength, the gamma rays and X-rays are completely absorbed by the atmosphere. So to observe so these are the high energy photons or high energy astrophysics as we call it. To understand anything about them, we have to go to space. And that's why we have several high energy astronomy telescopes in space currently, and with India also contributing to it through the AstroSat telescope, which can collect the gamma rays and photons. These are very complicated things to do because the interaction cross section of these energetic photons is quite small. So you need to build very complex detectors to collect the photons from it. And there's also a slight shift from quantum mechanics to classical mechanics, because in the higher frequencies, you treat these as photons, as particles. But as you go to higher and higher wavelengths or lower frequencies, you start treating them as electromagnetic radiation. So the wave particle duality also comes in, and that's how you also have to design your detectors. So visible bands are open. Infrared, now if as you go to slight push towards the higher wavelengths, infrared bands again are absorbed by the atmosphere, mostly by the water vapor. So even for infrared telescopes, you can do two things. You can either go high up in the atmosphere using, say, a balloon, for example, or you can mount the telescope on a plane. And if you have ever heard of this SOFIA instrument, SOFIA, what they do is they have taken a standard Boeing plane and then an aeroplane and cut out the last bit of it to have an aperture which opens up and has a telescope, an infrared telescope inside it. So during its flight, it goes and observes the cosmos. Or one of the most well-suited telescopes are in space, actually. The best infrared telescopes are in space. And then as we go towards higher wavelengths, as you go to the radio bands, the atmosphere again becomes transparent. Okay, so these are the kind of things that you must have a feel for, which are the transfer. So this decides whether you can have ground-based instruments or you need to go to the space. And having a broad band of wavelength coverage for any given physical phenomena is absolutely essential. As I will discuss soon, given a astrophysical object, it can emit over a broad range of wavelengths, from extremely high energy photons to at very wavelengths, very long wavelengths as well. Okay, so this is the transmissibility of the EM spectrum, and this is how we decide what to observe and where to observe it from. Then, of course, comes this concept of continuum emission versus line emission. As we all know, that emission from a given system, from a quantum mechanical point of view, is essentially just transition between two states. If you have two discrete states, the emission frequency is discrete and finite. Of course, you have quantum mechanical probabilities, and of course broadening due to other factors which I'll come to later. But essentially, from the point of view of atoms, it is just transition between two states. However, the states can be continuous, or the difference between the different states can be very small. And that is why you have many different transitions, slightly different frequencies, giving you a continuum emission. So there are two kinds of emission processes, and we'll talk about this as we discuss the various kinds of emission mechanisms. One is called the continuum emission. In the continuum emission, the given physical object emits the radiation over a wide range of wavelengths or frequencies. Okay, so it's not just transition between two particular states. And I will give you an example of how you can generalize between this quantum mechanical sense to the continuum sense, where if you have a quantum mechanical system between two levels, of course, from level 2 to 1, if something comes down, it emits with the given frequency, plus minus delta mu, because of these uncertainties. But what happens if the energy of there are many different levels. So between two, near about two, you have level 2, you have many other levels. So there can be many different probabilities of transitions, and all of these probability transitions actually coalesce together and become a continuum emission. So I'll as I discuss the various kinds of emission mechanisms, this will become much clearer. But what is important about this continuum emission is how, when we observe something or a spectrum from from a astrophysical source, how that spectrum looks. For example, this is a typical spectrum of an active galactic nuclei. And the paper that I've taken it from is Zeng 97. Again, nothing special about the spectrum. I just wanted to demonstrate how the aging spectrum looks like. You can firstly see that there are many spiky structures here, and each of these spiky structures correspond to one given emission line or a complex of emission line. For example, this is O3 plus N3, this is silicon 4 plus O4, etc., etc. The reason is because the emission frequencies of these two lines are very close together. So when you see the total emission, you see a blended feature of both these lines. You need higher spectral resolution to distinguish these lines. But what you see here is there is a general trend in the baseline of these emission features. For example, you have these spiky features, but there is a general trend here. So the base from which it rises, that has a falling slope with wavelength. For example, on the other hand, here on the below 1000 angstroms, you have almost like a flat line. So the emission here, and by the way, the emission is not zero because you are still receiving some amount of energy in these wavelengths, but you don't have them in the form of finite lines. So these transitions are due to discrete transition between two discrete levels, and that's why these are emission lines. But these are continuum emission due to several kinds of processes. For example, in an AGN, the central continuum emission is decided by what happens in the accretion disk around the AGN. Now, photons from the accretion disk are usually being emitted from the hot plasma that is swirling around the black hole, and it is heated up. And it's essentially thermal in nature. And many of you have already known about what is a black body radiation. So different layers at different radius from the black hole, you have different temperatures of this of the fluid that is moving around, and that is called the black body in the plane of the disk of the accretion disk of the disk black body, or a multicolor black body. So this thermal photons then go and interact with the cloud of hot energetic electrons surrounding this accretion disk that is called a corona. And as they interact with them, there are compound processes where it scatters with the hot electrons, and as in this process, it further gives out more energy. But these scattering processes, or the emission from the black body, or the thermal plasma in the accretion disk, they are not at a given particular frequency, but spread over a wide range of frequencies and wavelengths. And that is what gives you this continuum shape that is underlies the basic spectrum, over which we have this strong emission because of some metal population in the galaxy, in the gas in the galaxy, that is giving out this strong emission line that are excited by the incoming photons from that galactic nuclei. So what I wanted to focus on is, when we deal with continuum emission, we have a fixed set of emission mechanisms, and this is one of the fundamental point of this particular lectures, where I will discuss some of the emission mechanisms giving rise to this continuum emission. I will not talk about line emission in particular, at least for this set of lectures, but give you a glimpse of how to deal with the basic formalisms of the quantum mechanical transitions that gives out a line emission. Okay. Well, I also wanted to highlight okay, this is also interesting. You can have emission lines, but you can also have absorption lines. What is an absorption line? For example, you have this nice laminal for forest over here. This will be taught to you in your cosmology course, perhaps. So I'll refrain from going too much into the details, except for showing you that in the previous line, for example, we had these spiky structures due to emission as things come coming down from level 2 to level 1. But you can also have the other way around, where a photon goes and interacts with an atom that is at the lower level and then gets absorbed as the atom is excited up to level 2. It can de-excite perhaps, but the de-excitation may not again come back to level 1, or the rates of de-excitation may be different from the rates of excitation. In that case, you have the basic continuum and it is getting absorbed. And this kind of dips in the spectrum are often observed. And these are called absorption features. So you can have emission features as well as absorption features. And this is how a typical spectrum looks like. All right, so this is the basics of of a spectrum from an astrophysical source. Now, I will talk about some of the basics of the mathematical formulation of how we can understand how energy when emitted from a given source, when it reaches us, what would be the ultimate flux of it. To define it, we will define some given some definitions of how to define the energy going into a particular direction. The first is specific intensity. Now, it's very important to note the exact definition of these, as the definition itself has a lot of assumptions into it. So specific intensity is the amount of energy that is going through a given area, dA, along a given direction that is normal to dA, into a solid angle d omega. So suppose there is an observer here, and observer is trying to understand what is the amount of energy that is going into this particular solid angle d omega. So d omega per unit time per unit frequency. So that is called specific intensity. So specific intensity, I knew, as it's called in a standard literature, is the energy divided by the area normal to the towards that particular direction per unit time, per unit solid angle, per unit frequency. So its units are ergs per centimeter square, per second, per steradian, per hertz. Okay. Next is, what is the amount flux? So flux is the amount of energy going through an area dA per unit time integrated over all the solid angles. So you have an area dA, but remember, for intensity, what we had assumed was the area has to be normal. So even if the area is at a slight angle, what we should consider is the normal component of that particular area towards that particular solid angle. So intensity essentially means the amount of energy going towards a particular direction. So there is a sense of directionality involved with the definition of specific intensity. Different directions have different rays going towards them. And with each ray, we associate a specific intensity. And the relation between the intensity and the energy emitted along that ray is given by this definition. So intensity is just the energy per unit area, per unit time, per unit solid angle, per unit frequency. Now, if you want to consider the flux, which is the total amount of energy that's passing through a given area, what you might remember is this particular area can intercept different rays going at different directions through it. So if you know the intensity distribution at this particular surface, the total amount of energy that's going through this particular area is just integrate over all directions or integrate over all solid angles. And of course, since the intensity is associated with the area that is normal towards that ray, while doing this integral, we must also consider the fact that this particular area will have a component, will have a normal direction along the direction n, normal component along the direction n. But the intensity along a given particular direction, when we want to define it or want to find the total energy, we must recast this area dA towards a normal component along this particular direction. So that is why we have to consider dA cos theta. So while integrating over all the solid angles, we have I nu cos theta d omega. So integrate over all solid angles. So the units of the flux is ergs per centimeter square per second per hertz. Now, there is a relation between the intensity and the energy density at a given point. So again, let us go back to the basic definition of specific intensity. So intensity is related to the energy, of course. So the total amount of energy, I'll just follow what is given in the text here in terms of the definition. The amount of energy per unit frequency that is crossing a particular surface area, dA, is delta A is just I nu d omega dt dA cos theta dA cos theta. This is nothing but just the rehash of this definition, except that we had the area normal to the particular ray. Now this area may not be normal, so we have to take into account that this should be dA cos theta. So come from normal area. So if we have the I nu along this particular direction, then the total amount of energy going in that particular direction is I nu d omega dt dA cos theta. Okay, and this is the energy per unit frequency, so that's why we're not writing the d nu over here. Now, suppose what we are considering is the amount of energy going along a particular beam. Okay, so if that beam is considered by the fact that we have an area that is dA and the area normal to this direction is dA cos theta, then what is the amount of volume covered by the radiation per unit time? The volume covered by the radiation is, so in unit time, it will go a distance, unit time dt, let's say, it will go a distance of c times dt, c is the speed of light. So the volume is just this area times c times dt. So this is the delta V of the volume. So the total amount of energy within that particular volume is given by this delta E nu. So this is the total amount of energy per crossing this surface in time dt. So in that time dt, the amount of energy that has crossed the surface and is within this volume is this delta E nu. Okay. Again, some basic definitions. There's nothing complicated about it. So if we want to consider what is the energy density or energy per unit volume, all we have to do is take this energy over here. Sorry, my cursor is not visible. Okay. Take this delta E nu, which is the amount of energy passing through this area and within this volume of delta V, and divide it by delta V. There are some slight conceptual points to note here. Firstly, this is the particular energy in a given direction. Okay, so there is a directionality involved here. So that is why this is the amount of energy density per unit solid angle. So U omega d omega. This is not the full energy density, because all we have done is calculated the energy that is going along a pencil beam along a given direction, which follows this definition of the I. So the energy density along that particular pencil beam, or which is E nu omega d omega, this is a function of solid angle because it's a function of direction, is I nu by C d omega. Okay. So the energy density as a function of direction, of course, at a given location is related to the intensity as U omega is I nu by C. This is very fundamental, and again, you will come back to it when we discuss black body radiation. So the total energy density, to find that, you have, of course, have to integrate over all the solid angles or integrate over all directions. What this means is that you can have a direction dependent or a theta dependent. Or so, for example, if you have a azimuthally symmetric system, which is phi symmetric, but that is varying in theta in a spherical coordinate system, for example, then of course you will have different values of the energy density at different angles from the normal to the particular area. And that is why you have U as a function of the solid angle omega. But the total energy density is you just integrate over all the directions. So this is I nu by C d omega. And this is just a different way of representing it. What we call it is J nu, capital J nu. And capital J nu is the mean specific intensity, which is you average over all the solid angles. So if your I nu or the intensity distribution is direction dependent, then you integrate over all solid angles and divide by 4 pi to get the intensity of the solid angle integrated mean specific intensity, which is called the capital J nu. So some key highlights to note here, which is the solid angle integrated energy density is proportional to J nu by C, or in terms of, think of it in terms of physical sense or units. Energy density is equals to the intensity divided by C. Okay. Now, this capital J nu you may not appreciate it right now, but there are several instances where this will crop up, especially, for example, if you are trying to understand the photoionization from a given source and the total amount of emission emitted from in different directions. We usually write it in terms of the specific intensity integrated over all solid angles. So this is how energy density is related to the intensity. Okay, maybe this is the last. Okay, I will take a pause here perhaps and see if there are any quick questions, a couple of questions. So if any of you have any quick questions, please raise your Zoom hand and I will address it. Otherwise, I'll move on to the next slides. I'll wait for 10 to 15 seconds to see if there are any raised hands. Okay, Vinisha Kalwani, please unmute yourself and ask.
Good morning, sir.
Morning.
So I wanted to know that in the beginning you said that certain radiations are absorbed by the atmosphere while others like visible light pass through. So what is the reason for this absorption?
It is mostly due to the atmosphere that we have. So the atmosphere is filled up with different kinds of atoms. They have different kinds of cross sections. And for example, water vapor is a very good absorber of the infrared emission, water vapor, CO, and everything. So the infrared bands are absorbed there. The high energy photons are basically absorbed because you have a dense absorbing, now not because of any particular element, but we have a dense thick atmosphere and it just scatters around, and before it reaches it scatters and gets absorbed by some of the particles, and its energy gets redistributed. So it's mostly because of the thick atmosphere. If you go to the moon, you will not have that. Okay, next question perhaps. Richik Bhattacharya.
Yes, sir. Sir, can you please once show the previous slide once?
The previous slide, okay. Just 1 second. Yes.
Yes, sir. Sir, here we can see that the formula for U mu is equal to, I mean, the total energy density is integral of I mu divided by C d omega, that is
Yes.
equal to 4 pi by C J mu. So from here we are getting that the C gets cancelled, and so J mu is equal to 1 by 4 pi I mu d omega integral. So, but in the next, I mean, it is written that I mu by C. So, am I missing something? So, shouldn't the
Okay.
C be there?
So okay. So sorry. Yes, you are right. JNU will not have I nu by C. That was a typo
It is
on my.
just I mu.
Yes, yes. JNU will just
Okay,
be
sir.
an integral
Okay,
over I nu d omega. Yeah, that is a typo. Thanks for
okay, sir.
pointing it out. I will correct that in my notes. Good, you noted that. Good. So you're not sleeping. Thanks. Okay. Pushti Shimankar.
Yes, sir. Sir, I have doubt that first you uh, put the formula about the total energy density along the pencil beam, and second one is summed over all the pencil beam. So I couldn't understand the difference between that.
Okay. So what you have to see is if the emission is isotropic, essentially there is no difference. But what happens, for example, if you have emission along a given direction that is more stronger. So, for example, you look at the spherical polar coordinate system. Okay, suppose the emission at theta equals 0 is strongest, but you have no emission at theta equals 90. That means that there is a profile in the emission, and that depends on how the emission is being generated by the physical process. So if you take different pencil beams at different angles, then of course the amount of energy along given beams will be different. So what I first talked about is this U nu omega d omega. That is the energy density along a given direction. So given a particular theta or given a particular direction, if you go along that particular direction and the radiation associated with it, what is the energy per unit volume along that particular direction? But of course, that this is different. So what we are trying to do is average out or find the total energy density in the entire field. So you integrate over all the angles and then find essentially sort of an angle averaging of the energy density. Okay, so you integrate over all the solid angles and then find out in the given volume what is the total amount of energy per unit volume, and that is what it gives you, the solid angle integrated or integration of all the pencil beams. So you can think of it almost like a angle averaging of the energy density, which is essentially a function of the angles. Okay, last question, Atul Kulkarni, please unmute yourself.
Yes, good morning, sir.
Good morning.
Sir, when we talked about continuum emission, is it that the emission is happening between the virtual states and real states that we study in case of scattering?
Can you elaborate what do you mean? What exactly do you mean by virtual states, real states? Let me understand what you
So
exactly mean.
like when there is emission between two real states, we know that like when we explain we need to explain the spontaneous emission. We take the help of virtual
Yes.
states, and we say that there are virtual states between two states, with real states. And
There are virtual states between two states.
So what I am talking about is mostly the real states. Okay? The concept of the virtual states is used just as a proxy to understand some of the emission processes. But of course, you can like think of it in that way. But mostly, I'm talking about the real states.
okay, sir.
Okay, so I've already corrected it. Thanks for pointing it out. See? All right. So going on to the next few slides. So this is just recapturing the standard inverse squared law that we know, but using it from the mathematical point of using the mathematical formulation that you've learned about the definition of this specific intensity. Now, suppose you have a sphere that has uniform intensity on its surface at a given radius r. So that is the I nu at this particular radius r is I0. So all rays that are crossing this sphere in the normal direction have the intensity I0. So what is the total flux? So this is a bit misleading, because intensity, as you can understand, is not really decreasing along a particular direction. And I don't think I'm showing the proof of this here. But intensity is just the amount of energy that is passing through a given pencil beam from point A to point B. If you have no addition of energy or no subtraction of energy, so if there is no emission or absorption, the intensity will remain constant. So if you just take the amount of energy that is coming from this point, along this pencil beam from this point A to point B, the intensity along this particular ray is constant. But as we all know, the total flux falls off as 1 by r square. So what's happening here? That is what we are trying to address here. So let us calculate. So given this definition of intensity, or that the fact that intensity is constant on the surface of the sphere, let us try to find the total flux at this particular point P. So again, just using the basic definition of flux is you integrate over all the solid angles, I naught cos theta d omega. Okay. Now cos theta is the cos theta that you make with respect to this particular area. So if you just take an area normal, this is the same thing. So for us, what we are doing is you're taking the theta, that is this is the normal to the point P, and we're taking the angle from this normal theta. But of course, not all of these areas of the sphere will contribute rays to the point P. So the point P will only see rays or only see points from the sphere up to which there is a tangent. So for example, this particular point will not contribute any ray to P, because the rays are all coming out perpendicular to it. Or essentially, you can think of it in a different way. If the intensity is I here, then the normal to this particular component has no contribution to it here. So when you do this particular integral, or when you integrate over cos theta, you go from 0 to theta c, then you are limited by this area. And just basic simple trigonometry, you can transform this sin theta c into r by r, and you recover this 1 by r square, a standard form. There's interesting points to note here. Once you perform this integral, what you get is the total flux at this point P is pi times I naught, which is the intensity distribution at this on the surface here, times capital R by small r whole square. So if you are farther away, that is the small r increases, you fall off on 1 by r square. But there is this additional factor of pi times I naught. So at the surface of the sphere, which is small r equals to capital R, you have flux equals to pi times I naught, which is very interesting. Now you have a nice relation between the flux and the mean specific intensity, or the specific intensity or constant specific intensity at a particular point. Again, we will use this relation later on when we use black body. But this was just a brief demonstration of the fact that the reason why you essentially have the inverse square law is not because the intensity along a particular ray is decreasing. That is not the case. But the fact that the contribution of a given area element towards your line of sight, that decreases drastically. Because as you tilt the particular normal away from your line of sight, the cos theta contribution of that particular area decreases, and it only exists up to a particular point, up to the tangent of the sphere. Okay, so good. We have recovered the standard inverse square law from the basic definitions. So now we'll build up on this and go towards the formulating a radiative transfer equation. So again, from the basic definition of this is again very similar to the intensity, but not exactly, as you'll see. First, well, what we'll define is the emission coefficient, J nu. And I must caution you that people often mix the emission coefficient with emissivity. Emissivity and emission coefficients are two different things, because there's slight differences in how you create the definitions. So this particular thing is emission coefficient, which is small j nu. And it is the amount of energy emitted per unit solid angle, per unit time, per unit volume per unit frequency. Okay, so essentially the difference between emission coefficient and intensity is we have per unit volume here, and intensity we have per unit area. So total amount of energy emitted by a given process in a unit volume dV is J nu times d omega times dt d nu and dV, of course. If emission is isotropic with power P nu, then power P nu means that energy per unit time. So so this is dE by dt. This is essentially P nu. So and this is per unit volume. So you can remove dV here. So J nu is just 1 by 4 pi P nu. 1 by 4 pi because this is essentially the solid angle average. So you have unit contribution from each solid angle. The reason why I state this here is because when you consider different emission processes, oftentimes it is much easier to calculate the power per unit volume, or if the emission is isotropic, for example, if there are no beaming involved, then all we do is calculate the power per unit volume, and then we can get a handle on the emission coefficient changing. So suppose you have a pencil beam going along a particular direction, and some physical process adds some energy onto the beam. So that will of course change its intensity. Okay, so the change in energy in the given span and given unit in the given pencil beam due to this process is given by this J nu times d omega dt k nu dA. So I had the volume here. Suppose the pencil beam has a surface area dA and is traversing a length ds, so the volume is dA times ds. Now I can recast the same definition in terms of the intensity, and again this is just follows from what I had defined just a few slides back. The amount of energy, the change in energy, let's call it as is related to this change in the specific intensity di nu. So this added energy, or the change in the energy, or the change in the intensity is di nu times d omega dt dA d nu. So if you relate these two, then you have an expression of what is the change expected in the specific intensity, which is di nu equals to J nu times ds. Yeah, this is a note that I've given here. It is interesting to remember this because if you have emission from, for example, let's say you have an object that is emitting isotropically in a different system in its rest frame. If that particle is actually traveling with very high speed, it becomes anisotropic. Okay, so you have to take care of various kinds of angular distribution of the intensities, and that is why this term involving the per unit solid angle that comes in here. And I will come to it when I talk about beaming of radiation due to fast moving charges. Next is absorption. Now, suppose you have some certain particles that can interact with the light or the electromagnetic radiation that is coming through that particular volume, and it can absorb the radiation. Participants, please keep yourself muted to avoid any disturbance for others. Please unmute when we ask you to unmute yourself. Okay, so suppose that a given ray of light is passing through a volume and it is getting absorbed. The radiation is getting absorbed by some particles here. So now we define an absorption coefficient, alpha nu, in this way. What we define is the change in the specific intensity is related to minus alpha nu I nu times ds. So from this, what you can understand, if you just compare the units, there is I nu on the left hand side and I nu on the right hand side. So alpha nu times ds will be non-dimensional. So ds is just the length of the path which is traversed, and then alpha nu is just inverse of length. Okay, so this is the alpha nu, and I will show you now in how it is related to the cross section of interaction. Now suppose there are n absorbing particles within this particular volume, and this particular volume is dA, which is the area, and times the ds, which is covered by the beam. So again, following from the basic definitions of intensity, the intensity at a given solid angle d omega that is coming out from this volume is, well, I talked change in intensity because some absorption is taking place. So if the incoming intensity was I nu, the outgoing intensity would be I nu prime, and I'm talking about the change in intensity due to this absorption process. So it is d I nu times dA d omega dt d nu, which is again the basic definition of the energy. So essentially what we're trying to see is amount of energy absorbed. But then we have n. So we have n particles in this system. Just let's talk about unit volume. So you have n particles in this particular volume, and each particle has an area associated with it, which is sigma nu, which is the cross section area. So the volume that is covered. So we'll assume that once a given cross section is projected by a given particle, the intensity from that region will be absorbed. So what is the total amount of volume that is? That sounds good. So what is the total amount of volume that is covered by these particles, which is opaque to the incoming intensity? So that is n sigma d and n sigma nu times ds. So sigma nu, of course, remember, is a cross section, which is in units of area, in units of per unit area actually. And this is multiplied by the ds, which is the path length along which it travels. And this multiplied by the total density is multiplied by the total number of particles per unit volume. So if you just compare the two sides, you will find that the change in the intensity is related to the amount, the cross section in this way, which is minus n sigma I nu ds. So if you are relating the scattering cross section to the absorption coefficient, the absorption coefficient is nothing but the number of scattering particles times the sigma nu. Okay, so people also define something else, which is the absorption cross section per unit density or per unit mass. So this is called the kappa nu, which is mass absorption coefficient, where you define it in this way: alpha nu equals to rho times kappa nu. Now you have two different sources by which the emission along a particular ray can change. One, if I go back to the previous slide, which is di nu, the change in intensity due to emission. So J nu is the emission per unit volume. Again, per unit solid angle and all the standard definitions. This times the particular area element or the length element along which you consider the ray. This gives you the change in intensity. So di nu is equals to J nu times ds. But then it can also get absorbed. So di nu is equals to minus alpha I nu ds. So if you are considering the change in intensity along a particular ray, you have an incoming intensity, there is some emission and absorption process. So now you can write out a differential equation. di nu ds equals to J nu minus alpha nu I nu. So this is the most fundamental equation in radiative processes. This shows you that given a particular direction, along a particular direction, if you consider, you can find out the change in intensity due to emission and absorption processes. Immediately what you can see is if there is no emission or no absorption, then intensity along that particular ray remains constant. Again, as I have demonstrated earlier, this does not violate the inverse square law, because for the inverse square, what we are essentially interested in is the flux, not the intensity. So these are some differences that you have to remember when we talk about this. So in the last few minutes, perhaps, I'll talk about a more generalized definition of the radiative transfer equation. This is following the book by Mihalis and Mihalis. So so what I've talked about previously was the fact that I consider the intensity along that particular ray to be constant in time. So there is no time evolution of the intensity that's going on. If you have a time dependent intensity field, then the full form of the equations has to be written in this way, which is 1 by c del I nu del t plus del I nu del s equals to j nu minus alpha nu I nu. So essentially what we have an added extra term is 1 by c di nu dt. So, which essentially gives you the change in intensity due to some process that is a function of time within that particular volume. Now we can recast. So one must remember that this particular equation is along a particular ray. When we are doing a computation in a particular in a domain, it's much easier to fix the geometry of the system and consider rays that are going in different directions. So if your coordinate system is fixed, then instead of integrating along a given ray, you would prefer to integrate along the given directions of the coordinate system. So for example, if you have a Cartesian coordinate system, you can just apply the chain rule and find and recast the derivative along the particular direction as del x del s del I nu del x and so on, etc. But if you remember from your basics basic of 3D trigonometry, del x del s is nothing but the direction cosines. So you can recast this particular term as direction cosines times the divergence term or the Nabla operator equals to j nu and I. Sorry, Avinash was unmuted. Okay, so this is the most fundamental way of writing the radiative transfer equation. Do I have anything? So I have the concept of optical depth and the solution of the radiative transfer equation. I have 5 more minutes, so I can perhaps go along with this. But in most of the cases, I wanted to introduce it because this is what you use when you actually do a time-dependent radiation field, which is what we need in, for example, say radiation hydrodynamics. But you will not, in most of your standard implementations, you will not require this term. You will consider steady state radiation fields, and you will just use the standard equations starting from this term here. So you'll mostly ignore del I nu del t, unless your emission source is, for example, changing with time. So if your system is changing with time, so that can happen if your emitting material is moving, for example, or the emission, there is some time-dependent phenomena happening in the emission mechanism. For example, the temperature is changing with time, perhaps. Or you have a central radiation source that is emitting radiation, and the radiation is passing through a given volume in space. The central radiation source itself is changing in time. In such cases, you have to use a full equation. So now we will talk about some of the solutions of the transfer equations. So first of all, forget the time-dependent part and also forget emission. Let's just focus on absorption. So di nu ds is minus alpha nu I nu. A very simple integral. You have this, which is an exponentially decreasing function. So what it shows is, if you have an incoming intensity and it is passing through a region that is purely absorbing it, the intensity decreases along that path length exponentially in this way, which is, and the integrand inside the exponential is integral over the alpha nu ds. This can be conveniently recast into something called the optical depth. So optical depth, the total optical depth from point A to point B is just the integral of the absorption coefficient along that particular ray. We can also write a differential optical depth delta and d tau nu, which is the for a small excursion along that particular path, what is the change in the optical depth? Okay, so the total optical depth is defined as from integral from S0 to S. S0 is the starting point along that ray, but d tau nu is just the small change in optical depth as you go from go bits along the particular path. So in this particular case, the intensity can be written as I nu times exponential minus tau nu. So you can understand if the optical depth is greater than 1, then your intensity is decreased or attenuated. And in such a case, it is called, the medium is called optically thick. If your optical depth is less than 1, you will still have a decrease in intensity perhaps, but very small. So essentially, the intensity, as a ray passes through that particular medium, the energy in the ray is not really affected much. So that is called optically thin. And whether a particular medium affects your intensity or affects the intensity coming from a central source that is far away from that medium is really affected by the optical depth. So calculating the optical depth is one of the fundamental things we also encounter in radiative processes in astronomy. And of course, optical depth can also be interpreted as in a probabilistic way. For example, you can think of it in this way: you launch a bunch of photons. Again, consider that volume of where the absorption was taking place. You launch a bunch of photons, and a fraction of these photons are absorbed by the observers, and a fraction of these photons reach the end of the volume. So in this way, now you're counting photons. So the total amount of photons absorbed divided by total number of photons that was initially thrown, and this gives it a probabilistic definition for the absorption event. So if you recast the intensity relation in terms of the photon statistics, the probability of a photon to travel a distance s with optical depth tau nu is e exponential minus tau nu. Again, this comes from this particular thing. So if you just recast it in terms of the photon densities of the total number of photons, then if you start off with a given number of photons, a certain fraction of photons are finally found at the end as it passes through the volume. So the probability is this divided by this is exponential minus tau nu. So the mean optical depth traveled is, of course, if you integrate over all the optical depth, so essentially you just integrate over the variable of the probability distribution, which is 1. So this nicely brings us to another feature, and again, many of you have learned it from the basic theory of the kinetic theory of gases, but this is another way of how you derive this quantity, which is a mean free path. So since the mean optical depth is 1, so we can also associate a mean length that is traversed by the photon without getting absorbed. Okay? So mean depth of 1 is alpha nu and L average, let's say. Again, this comes from the basic definitions of optical depth. So the mean free path, or the path along or the distance traveled by the photon without getting absorbed, is just 1 by alpha nu. Again, this is from the basic definitions of probability and how you can relate the mean free paths to the absorption coefficient or the cross section. Maybe this will be my last slide for today. I'll just sketch how you can actually solve the radiative transfer equation for a generalized system when you have both emission as well as absorption. Now we saw just now that if you have absorption and no emission, the solution is a simple exponential function. However, if you also have emission along with it, then the situation becomes slightly a bit more complicated, and then we recast the equations in a different way. So this is the basic starting equation of radiative transfer, the time-independent radiative transfer. What we do next is we take the alpha nu, or the absorption coefficient, and divide it on by both sides. So on the left-hand side, we have di nu divided by alpha nu ds. And on the right-hand side, we have minus I nu plus this term, which is the ratio of the emission coefficient to the absorption coefficient. Now, this in the standard definitions of or the literature of radiative transfer has an interesting name called the source function. What it shows you is a ratio of the total amount of emission that is added to the to a particular ray divided by the amount of radiation that is taken out of the ray. And you will learn more as I relate this to the black body, how this is related to the black body distribution soon. So now you have a nice differential, and of course we on the left hand side we recast the main variable in terms of the optical depth. So instead of integrating along a space, we integrate along the optical depth. And this is again a very standard way of expressing things. And you will find most of this often comes up. For example, you are studying stellar atmospheres. Okay, so it can be two-way. One is the emission coming from inside the star that is going outside. You can also have a different situation where you have emission outside and you have an atmosphere and the emission is coming inside. So in any of these cases, what we actually do is instead of finding the emission or defining the intensity as a function of the length or distance, we define it as a function of the optical depth or the column depth. We can always retransform back from the optical depth to the depth or the length along that particular ray by this transformation if we know the alpha nu. So if we have this equation, then the solution can be found by using an integrating factor. I'll not go into the details of it. You can find it from the PDF of the notes that I will share with you. But the final solution will look something like this. This is interesting. So take a moment to understand what is happening here. So first of all, forget the integral term here. I knew at the end. So let's say we start from point 1 to point 2. The optical depth at point 1 is tau 1 and the optical depth at point 2 is tau 2. So you have the intensity entering the point 1, which is I nu, and again, instead of S1, I call it tau 1 because I find the optical depth at that particular point. So if that intensity and if there is no emission, so this is just integral over the source function, okay, and the source function is J nu by alpha nu. So if there is no emission by the ray, by the volume as the ray passes through it, you again recover the standard exponentially decaying solution. However, if you have an emission that is being added onto it, then you have to integrate over the source function in this by this added term here. Okay, so for a constant source function, for example, you have something like this. So now let us look at try to appreciate what is happening here. So I did nothing here except let's just perform this integral over the exponential function, assuming the source function is constant. Source function constant meaning J nu and alpha nu are independent of space. They are just constant along a particular volume. So you have this solution over here. Now let's try to understand the implications of it by taking some limits. So for example, if tau 2 minus tau 1 tends to infinity, for example, if the tau 2 or the point 2 is deep within the star, okay, or deep within a particular volume, such as the optical depth is very large. In that case, the intensity at the point tau 2 is nothing but the source function. So at that particular point, the point 2, any information about the incoming intensity is completely lost. This is very interesting because what we started off is a ray of light that is bringing some intensity as it enters the point 1 and it's going towards the point 2, and physical processes are happening that is adding or subtracting emission out of it. However, as you see here, if you go to regions which is deep, where the optical depth is very high or deep in the optical depth space, then you completely lose any information about the incoming intensity. What's happening here is the incoming intensity is completely absorbed by this term, and whatever remains along this ray is just the emission that is and the absorption processes that is happening due to the material that is emitting or absorbing the radiation. And this is a fundamental property of the intensity inside a region that is optically thick. So optical thick, as I said, is when the tau is greater than 1. So suppose the tau 1 is very small, the optical depth at the point 1 is very small, and you go inside a region that has very high optical depth. So it is optically thick. Inside that region, the intensity is nothing but the source function. So you can completely forget whatever the incoming intensity was because that is irrelevant now. And you can, if you want to do a radiative transfer calculation, You can immediately write the intensity inside your optically thick region as the source function at that particular point. Okay, so I think I will stop here and we'll discuss black body next week. Any quick questions? I have run over my time. Any quick couple of questions? Or you can write it in the Google Sheet. Yes, Mohammad Rehan, please unmute yourself and ask question.
Sir, absorption coefficient also dependent on other factors
What other factors?
like wavelength.
Yes, yes. As I have said here, the absorption coefficient is with a subscript of nu, alpha nu. Again, once I relate it to the microphysical process or the quantum mechanical process, you will see that the absorption process is nothing but when you have a transition from a higher level to a lower level. And of course, this is frequency dependent.
So therefore, some frequencies absorbed from the atmosphere.
Yes, that's right.
Okay.
Akshat,
Hello, sir. Good morning.
morning.
Sir, what does it mean for the emissivity to be isotropic or anisotropic?
Okay. So, for example, I'll give you an example in this way. Suppose a particle is emitting energy equally in all directions. Okay. So, for example, you have a thermal ball, and now thermal ball is it's just giving out luminosity radially outwards everywhere. So there is no directional dependence of the emission. Now, suppose I make the ball move very fast, and if you have done special theory of relativity, you will know that your emission going along a particular direction will get beamed, and I'll come to it later on. So, from the point of view of someone for whom the ball is moving very fast, the emission is no longer isotropic, or emission is no longer equally distributed in all angles. Emission is more distributed towards a particular direction, which is along the direction of the ball, as compared to the other angles. So in that case, the emission becomes highly anisotropic. Okay. There's a different way of looking at this. For example, you're trying to find out the emission from a particular region, but that region is covered or shrouded by a disk of matter that is falling in. A typical scenario is, say, emission from the accretion disk near the black hole, and the accretion disk is surrounded by a cloud of gas, which is also in the form of a disk. So an observer that is seeing it from the top will completely see all the emission. So that at theta equals 0, let's say. But the observer that is in the plane of the disk will not see any emission, because all of it is getting absorbed by this cloud of gas that is surrounding it. So that's why when we have the intensity distribution, it is not equally distributed at all angles, and that's why you have an anisotropic and isotropic emission.
Okay, sir. Thank you.
Spandan Joshi.
Good morning, sir. Sir, I wanted to know, in the expression of optical depth, what is the difference between S and S dash?
In the expression of optical depth, you mean here?
Yes, sir.
Oh, okay. S dash is just an integral variable. S is, of course, the path length along the particular ray, but we are integrating over the path length. So S prime is just in an integral variable that is changing. And S0 to S is, for example, let's insert a line here. I hope you are able to see my line.
Yes, sir.
Okay. Now let me insert S. Okay, this is S, the starting point. This is S0, the end point. And we are essentially just integrating over this path length, which I call as S prime, which is the integral variable. So these are the, it was oppositely directly, sorry. S0 is the starting point on this path length. And this path length you can keep on increasing. For example, I go up to a particular distance S, starting from S0. I can keep on going further and further. Okay, so I can keep on increasing S. So for example, it was 1 meter and I go to 2 meters, etc., etc. S prime is just the integral variable along this path.
Okay, sir. Thank you.
Okay. Thank you, Spandan. I think we're out of time. So if anybody else has any other questions, I'll ask them to put in the Google form and we can address it in tomorrow's lecture. Thank you, everybody. Santosh, if you're still there, I will log out and I'll let you handle with the next speaker.
It's okay. Yeah, I think we can
okay.
end the lecture and rejoin.
Okay.
Thank you.